All right, the limit comparison test for convergence. Now you'll see right away that the word comparison is in there, and that's also the name of the other test we just learned, the comparison test. So it turns out this is basically doing the same thing. It's going to allow us to compare one sequence or one series to another series. So if we know we have a divergent series, we can compare it to this one and maybe we'll figure out that ours is also divergent. Or if we think ours might be convergent, we can find a series to compare it to that also converges, and then this allows us to prove that they both converge or both diverge or whatever. So the advantage of this one is that it's a little bit more mathematical. So whereas in the comparison test, you'd sort of have to list out every term and show that they correspond or match up or whatever. And it was sort of like a logical, oh, it looks like it should work kind of thing. It was more about words and less about just plugging and chugging through a formula. So that was a little bit annoying about that one. Whereas in this one, we're really just going to plug in and find a limit, the answer to a limit problem. And if we get a number that's not 0 and not infinity, they both converge or both diverge. If we get 0 or infinity, that means it was an inconclusive test, that we're not sure, it wasn't a good comparison. So the advantage of this test, and the reason you'd want to use it instead of the comparison test, there's two reasons. One is that it's more mathematical and you can just plug and chug. And the other reason is it's going to work in those gray areas where the comparison test didn't work. So when we talked about the comparison test, recall that the comparison test, your series has to either be smaller than a convergent series, or your series has to be bigger than a divergent series, or else it doesn't apply. So the comparison test didn't apply if your series was larger than a convergent series or smaller than a divergent series. Because saying you're smaller than infinity doesn't tell you much, and saying you're bigger than 0 doesn't tell you much. This one, though, accounts for that. So this one, you don't have to worry about whether your series is a little bit bigger or a little bit smaller, term by term, than the series you're comparing it to. You'll still get an answer. The downside, so those are the advantages. Plug and chug, and you don't have to worry about whether it's an ambiguous case or whatever. The problem with this one, and the disadvantage of using it, is you have to come up with a series that's pretty close to the series you're testing. So for example, at the end of the comparison video, we did 1 over n to the n, sum of that from 1 to infinity. And it turned out that you could compare this to almost anything, and you could prove it's convergent. So you can compare it to a p-series, a geometric series, almost any p-series, almost any geometric series. This thing gets so small so fast that you can compare it to almost anything and get an answer from the comparison test. But when you're doing this limit comparison with the ratio, unless you pick just the right thing, you're probably going to get an ambiguous answer. So I just want to emphasize this again. You're going to take the limit of your series divided by the series you're comparing it to, and that limit needs to be a constant. It can't be 0 and it can't be infinity. So if you get an answer, if you plug and chug through this limit problem and you get 0 or infinity, it's ambiguous, it's inconclusive, whatever. You need to find something else to compare it to. You basically compared apples and oranges if you get one of those answers. So the problem is that unless you come up with a pretty good apple to compare to your apple, you might get an answer that doesn't work out. So that's the one disadvantage of this technique. But when it does work, it works pretty well. So for example, on this one, we've done this in a previous video also, but let's do it again. This one, we're just looking at it, you're like, you know what? That looks a lot like a harmonic series, just 1 over n. So I'm going to compare it to 1 over n. Now in the previous video with the comparison test, we had to worry about whether 1 over 2n was a little bit bigger or a little bit smaller than the harmonic series. But this one we don't. We're just going to take, we're going to say the limit as n approaches infinity, and we're just going to put the limit of one formula over the limit of the formula of one series over the formula of the other. So, let's call our series A, and we'll call this series B. So we're just going to put the a sub n formula, which is 1 over 2n, over the b formula, which is 1 over n. And what do we get? Well, let's see. Depending on how much you like fractions in algebra, I would just flip this and multiply, so we get, invert and multiply is how you multiply fractions. So you get 1 over 2n times invert the bottom, so the n's cancel, and we just get 1/2. Because if there's no n's to plug in anymore, so our limit is simply 1/2. So do both of these converge or diverge? Yeah, we satisfied the test. The test was we want to get an answer besides 0 or infinity. And 1/2 is a constant. It's not 0, not infinity. Therefore, the test worked, meaning that both the series either converge or diverge. And since we know that this one diverges, because it's the harmonic series, then this one also diverges. So pretty cool. That's an example of the limit comparison test working really great. Just do the ratio, take the limit, get a number. Doesn't matter what the number is. It lined up, everything worked great, they both diverge. Pretty sweet. All right, what's the deal with this one? So this is one of those ones where it might be a little bit tricky to figure out what to compare it to. But of course, as you probably noticed, we usually want to find either a geometric series or a p-series to compare it to. So again, the way to look at this is sort of look at this as a limit problem and think about what happens when n gets really big. Because we're going to be taking the limit as n approaches infinity. So the question is, as you get towards infinity, a lot of stuff starts not mattering, right? As you get towards infinity, that -1 is sort of like insignificant. So if you sort of ignore everything except the highest power upstairs and downstairs, really, this is the same thing as n squared over n to the 4th. Because that -1 doesn't really matter much. And of course, that reduces to 1 over n squared. So my guess is that a good thing to compare this to is 1 over n squared. Because as you get really big n's, that -1 sort of goes away, and this reduces to 1 over n squared. So let's take a look. So again, we don't have to know right off the top of our heads if we made a good choice or didn't. It's going to come out when we take this limit problem. We're either going to get an answer or we don't. So at that point, we'll find out if we did it right or not. So now we need to take the limit of the a formula, which is n squared over n to the 4th minus 1, divided by the b formula, which is 1 over n squared. Now your teacher may call a and b different things. I mean, maybe I'm calling the top one a, the bottom one b. Maybe your teacher would call this a and call this b. Doesn't matter. Either way, we'll get a number. I say potato, you say potato. I would get 1/2 maybe, and you get 2 over 1 instead. But either way, we got a number and not 0 or infinity. So let's just invert and multiply as usual. So you get n squared over n to the 4th minus 1 times n squared over 1. And of course, this is still the limit as n approaches infinity. So what's the limit of this puppy? Well, let's see. Oops, not n squared. N approaches infinity. N squared times n squared is n to the 4th. And downstairs, I get n to the 4th minus 1 times 1, which is still n to the 4th minus 1. So what is this limit? Anyone? Well, if you do L'Hopital's, you would get 1. The other way to do it is to say, you know what? You can ignore everything except the highest power of n upstairs and downstairs, and this reduces to just 1. So the limit is 1, and it wouldn't matter if it was 1 or 2 or 5 or 1/2. The point is it's not 0 and it's not infinity. Therefore, the test worked. We got something, a constant. We got a number, and therefore these both converge or both diverge. So which one is it? Does the thing I compared it to converge or diverge? Well, it's a p-series, and that 2 is bigger than 1, so it converges. So recall that when you're looking at p-series, which is basically n raised to a constant exponent, if that exponent is bigger than 1, it converges. If it's less than 1, it diverges. And if it's equal to 1, we would just have the harmonic series, which also diverges. So p has to be bigger than 1. But since p equals 2, because it's n squared downstairs, it's a convergent series. All right, another limit comparison test. Wow, this one looks funky and messy, but hey, what the heck. So what on earth should we compare it to? Well, you know what? Hard to say, because I want to compare it to something that's pretty easy to compare to, right? So I want to use something I know. So I need either a p-series or a geometric series. This has 2 elements. It has this right here is sort of a geometric series, because if you had 1 over e to the n, this would be a geometric series. And that would be convergent because you have an r less than 1. Your ratio in this one is 1 over e. And then there's another series we could compare this to instead, which would be a p-series. of n squared. Because n minus 1 squared, n squared, basically the same thing. So which one should we compare it to? I don't know. Let's try both. We can't compare it to 2 at the same time, unfortunately. We can only compare it to 1 at a time. So first I'll compare it to the geometric series, 1 over e to the n. Then I'll try comparing it to 1 over n squared, and we'll see if we get different answers. So first I'll take limit as n approaches infinity of my formula. Compared to the geometric series that I know converges. Let's see, so on this one, e's to the n cancel. I just get 1 over n squared. And remember, I'm taking the limit as n approaches infinity. So if I plug in infinity for n, I get 1 over a really big number, which is 0. Uh-oh. Recall that there's 2 things I'm not supposed to get when I do this comparison test. I'm not supposed to get 0, and I'm not supposed to get infinity. I just got 0. So this test did not work. Cross it out. Whatever the opposite of a check mark is, that didn't work. All right, so that was a bummer test. Invalid test. Because we got 0. So this time let's try comparing it to 1 over n squared. So I'll take again the series I'm supposed to be testing for this problem, and I'll compare it to n squared. All right, so this one isn't quite as easy to see, but we'll basically invert and multiply again. So we'll get 1 over e to the n times n minus 1 squared. And then I'm multiplying by, if you switch it, you get 1 over n squared over 1, which is just n squared upstairs, right? So this is the fraction. This reduces to this fraction. So the question is, what's the limit as n approaches infinity? Well, n squared and n minus 1 squared are both the same number, basically. They're both infinity, right? So n squared and n minus 1 squared, as n gets really big, the minus 1 becomes insignificant. So it's basically n squared over n squared, so those cancel as n approaches infinity. And we're stuck with 1 over e to the n, which is approaching 0, because e to the infinity would be infinity, but it's downstairs under a 1. So we get a limit, 1 over infinity, which is 0. So once again, we do the ratio test against this series, and once again we got a 0. So it didn't work. It's an invalid limit comparison. We don't want to get 0, don't want to get infinity. And just in case you're thinking, what if we switch a and b? I could run the same experiment again. This time I'll once again compare it against 1 over e to the n, let's say. But this time I'm just going to switch a and b, because remember how some teachers do a and b this way and some do it that way. So maybe if I switch the numerator and denominator, maybe that'll give me some luck. So instead of putting 1 over e to the n downstairs, I'll put that in the numerator. And I put my big formula downstairs. See, e to the n's cancel. I just get invert and multiply, I just get n minus 1 squared. The limit as n approaches infinity of n minus 1 squared. And that is what? Infinity squared is infinity, so I got infinity. So it turns out that's actually the reason that theorem says you can't get either 0 or infinity. Basically all that's saying is if you put a over b or b over a, if it's an invalid test, you put it one way, you'll get 0. You flip it, you'll get infinity. But either way, it's the same 2 things you're comparing, right? It's not a good comparison. So if you get 0 one way, you'll probably get infinity the other way. But either way, you're kind of hosed. It turns out that for complicated formulas like this, where it's sort of like a power series times, a p series, totally different from power series. A p series times something else, like a geometric series or something. Whenever it's a combination of different things, you're almost always going to want to use the ratio test, because it's really hard to find a valid comparison like this. Or in this one, we probably could have used the comparison test, because I bet you that since this denominator is so large, it's both a ratio test. You know what I bet? If we just compare this to 1 over e to the n with a regular comparison test, this sequence gives us 1 over e to the n times some stuff. So of course, if you compare it, every term of this is going to be bigger than these terms, because they have the same denominator, except our sequence has an n squared in it as well. So like we'll get 1 over e for the first term of both probably, but then we'll get 1 over e squared times 4 or something, whereas on this one we'll get 1 over e squared. So 1 over e squared times 4 is obviously smaller than 1 over e squared. So just from a straight comparison test, it's actually easy to show that this thing converges. But with a limit comparison, it's really hard not to get either 0 or infinity. All right, so here's another one we want to do a comparison with. So the question is what to compare? I'm thinking it's probably harmonic. You know, the harmonic's a good go-to. And just looking at it, there's kind of a funky formula. It's got 1 over n plus the natural log of n. But the natural log of n is going to be smaller than n by quite a bit, because it's like a log. So pretty much, even though this term is not insignificant, it's quite a bit smaller than n when you get into big numbers. So I'm going to go with 1 over n as being a good comparison. And of course, I don't have to know off the top of my head if it really is a good comparison. It's just the first thing I'm going to try. So I guess I don't need an equal sign. So I'm just going to do the limit comparison test. So there's a limit as n approaches infinity of one formula, 1 over n plus ln of n, over the thing I want to compare it to. Invert multiply. And we get 1 n over n plus ln of n. All right, so now just looking at this, you might be thinking to yourself, man, that's rough. Now I have enough experience with these that I'm sort of like, you know what, the natural log is smaller than n, so I'm pretty sure it's going to converge. But nonetheless, you know, me saying it so doesn't make it so. So we do need to come up with some sort of mathematical way to show or demonstrate that this, you know, what this limit is. Because I'm guessing it's going to be about 1, but I'm not totally sure. So let's use L'Hopital's rule, which is awesome because all you do is take the derivative of the top and bottom and it'll have the same limit. So remember, when you use L'Hopital's, it is not a quotient rule. We're just taking the limit of the top on its own. So the derivative of n is just 1. And then we're taking the derivative of the bottom totally separately. The derivative of n plus ln is going to be, derivative of n is 1. And the derivative of natural log is 1 over n. All right, so now we can see very clearly that, oh yes, indeed, as n approaches infinity, this term, 1 over infinity, just goes to 0. So our limit is just 1. And what that tells us, now remember, that limit is not the answer. All this says is that, yes, indeed, we just satisfied the limit comparison test because we got a number. We didn't get 0 or infinity. We got a nice constant number. And therefore, both these series we were comparing, they both either converge or diverge. They both do the same thing. And since the one we're comparing it to, the harmonic series diverges, therefore the one we're comparing must also diverge. So therefore, they both diverge. So that's the whole point. We just want something, as long as we get a number out of this limit, we know we did it right. And we can just say, hey, they both diverge, both converge. And of course, we picked, very deliberately, we picked something that we know whether it converges or diverges. If I pick something like 1 over, and you know, if I looked at this and I said, hey, you know what, I think I'll compare that to like n factorial over n plus 1 squared factorial or something crazy, this doesn't help me any, right? Because even if I did the limit comparison test and got like, oh great, this limit equals 2, that doesn't help me any because I don't even know if this thing converges or diverges. So knowing that my original series does the same thing as that doesn't help me. The whole point of comparing two things is you got to compare something you don't know if it converges or diverges to something you do know if it converges or diverges. And that's why we're always comparing things to either the power series or a geometric series, I'm sorry, P series or a geometric series, because, you know, it's not helpful if you use something you don't know the answer to. All right. Last one we'll do here. So what should we compare it to? I'm thinking geometric series, because I've got a constant. This doesn't, you know, e to the n doesn't necessarily look like a geometric series to most people. And it doesn't look like that to me either, except if you think about what a geometric series is, the real tell, the giveaway that you're looking at a geometric series, is you have a constant raised to a power of n. And e is a constant. It's 2.7 something. So I'm going to compare this to the geometric series 1 over e to the n. And since e is, 1 over e is my ratio in this particular series, and that's a number less than 1. So this series converges. So if I do my limit comparison test and I get, I get a confirmation that the test worked, then they'll both series converge. So to do the limit comparison, we're going to take the limit as n approaches infinity of our thing, which is ln of n over e to the n, divided by the series we know, which is e to the n, 1 over e to the n. Alright, so if we do this, the e's to the n's cancel, and we get ln of n. Limit as n approaches infinity of ln of n. Alright, so what's the answer to that one? Uh-oh. That's infinity. Bummer. So this is basically the test did not work, right? We needed a constant. Getting infinity or 0 screws us up. And unfortunately, I don't see anything else I could compare this to. So it looks like we've got a situation where the limit comparison test is not going to help us. So this is probably a problem that would be better served with the ratio test or something. Because the limit comparison test, my only shot was this one, was the geometric series, and I don't see how I'm going to be able, I'm going to get anything other than infinity here. So stick around for the ratio test, which is going to turn out as sort of like, it just works really well for so many types of problems, especially if you have factorials or weird complicated terms. The ratio test is kind of the way to go. So stick around for that.